Okay, then welcome back everybody from lunch. I hope you're not too sleepy after all of that food. And we will continue with a BGP fork in the row. And let's see the tale of the two implementations. Have fun.
Hi all, I'm Patrick. Together with Surya and Jaime, we are working on Oven Kubernetes. It's CMS for Oven, so we translate Kubernetes concepts into Oven logical entities and such. And today we'd like to talk to you about how we ended up with two BGP implementations. So we have one in OvenK, and there is one, the native one in Oven. So some time back, we found ourselves at a crossroads where we wanted to integrate BGP into OvenK, but there was nothing available. We knew that Oven is working at introducing BGP integration in the product, but we had to make a call whether we wait and try to work with the community or whether we want to go our separate way. As you may know, we've decided to do our own implementation, and today we'll try to describe how we did it, what are the differences with how Oven does it, and whether we can converge, and what would it take. So let's go to the left path and see how Oven does it today. I'm going to briefly describe the high-level concepts. I won't go into any major details, but I want all of us to have a common understanding what does Oven do. So at a very high level, and the main principle we need to keep in mind is that OVN is BGP implementation agnostic. So it doesn't matter what's your BGP implementation. You can use FRR, you can use BIRD, and Oven doesn't care. Oven doesn't talk BGP. What you can see with the green and red arrows is that Oven allows you to redirect the BGP control plane traffic into a VRF that would actually run your BGP daemon. So this means that there is no direct interaction, or Oven doesn't directly interact with your BGP implementation. It allows you to bring your own, but that also means that you need to pre-configure your BGP. So you need to make it so it works well with what Oven expects. And Oven handles it by creating netlink connection with the VRF, where Oven controller reads and writes routes into that VRF. And then later on, the BGP daemon can talk BGP control plane, advertise routes, and install the routes into the VRF for further processing. Let's get a little bit into how advertising routes works in Oven. So you have your NBDB, you have your routes there. You can configure your router so it is going to advertise those. What that's going to do is it's going to populate the advertised route table in SBDB. From there, Oven controller would read those routes, and using netlink, it's going to insert the routes into the VRF. The routes are going to be black hole, and an important bit to note is that they will have the 84 protocol, and that protocol is Oven route protocol. So there is a distinction for Oven controller, and it uses it to filter out the routes it installed itself by looking at the protocol and setting it up when it installs the route. And then from there, the BGP daemon is configured to consume those routes that were installed by Oven and advertise them outside. It's a very similar story for learning routes, just the other direction. The BGP daemon learns the routes, it inserts them into the VRF, then Oven controller reads those using netlink and programs them into the learned route table in SBDB. One thing worth noting here is that you cannot see any arrows pointing back to NBDB, and talking to the Oven maintainers, that's on purpose. So NBDB is mainly focused on what the CMS wants to program, and Oven tries to avoid programming NBDB itself. So it might be surprising, but there is no, the routes that are learned are not reflected in NBDB, but they will be present in SBDB. A major piece for us is the VRF management. So prior to very recently, there was a strict requirement that any VRF that you brought in to use as your exchange layer for BGP routes had to use an ID that was an exact match with the tunnel key configured on the logical router data bus. This was recently changed, so now the VRF ID is something that a user can set and control, and this is the new option that allows you to do it. So thank you, Alesh. Yeah, just to summarize, the biggest part of it is that OVN is BGP agnostic. So you bring your own BGP daemon. You have to pre-configure it to read the routes from the VRF and install the routes into the VRF. And there is no direct interaction between Oven and your daemon. And something that is important for Oven Kubernetes is that VRF today in Oven is only used to exchange routes. There is no data plane traffic flowing through that VRF, which is a bit different from what we do in OvenK. And by default, the routing information is confined to that VRF, and the default routing table is not affected. I'll hand it off to Surya, and we'll learn more about OvenK.
Thanks, Patrick. And I will be talking about Oven Kubernetes' journey of how we did BGP. I'm not exactly sure why the Oven Kubernetes path is all dark and cloudy with thunder, while the OVN one seems to be shiny and bright. And we are in a room with majority OVN and OVS contributors, so that's what we get. Anyways, joking. We just wanted to make a nice animation, but now we'll tread down that dangerous path right now. So let me take you on that journey. So with our 1.1 release in Oven Kubernetes, we have added support for BGP. And who in the audience is not familiar with Oven Kubernetes? Because we keep mentioning OVNK, Oven Kubernetes. Would you appreciate a quick intro? Just a quick raise of hands. You don't have to be shy. Okay, all of you. Okay. Yeah, I can do a. So Oven Kubernetes is a network plugin, a robust networking plugin solution for Kubernetes clusters. We are using OVN and OVS at its core, and OVN for our abstraction layer, and OVS underneath it as the data plane. So OVN and OVS are Linux Foundation projects, but Oven Kubernetes is a CNCF project. We just became Sandbox last year. So it is one other such CNI in the ecosystem, just like we have Selenium and Calico and other network plugins. So if you have a Kubernetes cluster, and if you want networking for your pods and workloads, Oven Kubernetes gives that to you. So coming back to the BGP support, we call it, in Oven Kubernetes land, it's called the route advertisements feature. It's just the name of the API. And that's what we give to the users to be able to import and export networks and routes, right? We'll see that in a moment in detail. In addition to OVN and OVS side of things, Oven Kubernetes also leverages FRR Kubernetes, which is another CNCF project as part of the Metal LB org to implement the BGP peering and configuration. So FRR Kubernetes integration is what handles all of that. And that underneath it is using FRR routing. So this slide might be a little bit confusing to all of you if you're not used to seeing custom resource definitions in the Kubernetes API. Do not be afraid. You do not have to look into every line of this slide or dig into the details. The takeaway points here are the concept of a network. A network in Oven Kubernetes, which on the left side you see, which is a cluster user-defined network or a user-defined network, as the name suggests. A user comes and creates a network. A network is the same as how you would picture this in the OVN land, which is a bunch of routers and switches connected together. So it's a logical topology. So every time me or Jaime refers to a network, that's what it means. On the right side, you see the route advertisements API. And this is what is the API that we give to the end users, using which they can leverage the BGP support. So it literally lets you advertise the networks that you select. So you can see a network selector right here. And that is having a match label thing that says advertise true. You can connect that back to the labels that I have here on the network. So that's the link between these two APIs. It's a RESTful API. You don't have to know all the details of the Kubernetes API, how it gets stored in etcd, etc. So like I said, forget the details. Just remember the two concepts that's what a network is in the OVN Kubernetes land, which is what it means to be in the OVN land as well. And then the route advertisements API is letting the users advertise those networks. An important part of the network to note is the CIDR. So we have the 22100, which I'll be using in the rest of my examples. And then this one is really tiny, tiny, tiny slide. I'm sure nobody in the back can see this. I'm sorry about that. But again, this is a second API, which is an implementation detail. It's called the FRR configuration API. So you might wonder, once the user creates the route advertisements API, what happens underneath? Like I mentioned, we are leveraging the FRR Kubernetes integration underneath it. So this API is owned by FRR Kubernetes project. And the route advertisements API is translated as an implementation detail by OVN Kubernetes controller into FRR configuration objects. And the important part to take away here is the to advertise and to receive things. So this is basically letting you use the FRR router. So it's exporting the FRR API to you. So it's letting you say what networks you want to advertise to the outside from your cluster and what networks you want to receive into the cluster from the outside. So TLDR, the route advertisements feature in OVN Kubernetes, aka the BGP support, is letting you advertise in-cluster networks to your provider networks and to import external networks into your in-cluster. So that's my TLDR diagram, like I said. So in a Kubernetes cluster, imagine you have multiple nodes. Each node is running an FRR Kubernetes daemon set. So that's what you see here. And that's what's responsible for all the peering to your provider edge router and provider network. And each network that I mentioned here, that you see the blue box with the 22100 subnet, is basically the UDN that I said, and that's what we are advertising. So advertise, export, slash, take it in, import. Looking at this in a bit more detail, I will try not to bore you with the details, but we can start from the bottom down. So like I said, a network, which is a bunch of pods in your cluster with that subnet, each pod gets an IP from this subnet, is attached to your BR-int bridge in OVN. So this is the NBDB database that I'm showing. We have the SPDB controller, etc. I don't want to go into the details of that. So we have the switch that the pods are connected to, and from here, based on how the user configures the cluster, we have two gateway modes through which the traffic flows. From the pod, if you want to reach the outside, we have a mode called the local gateway mode. And what it exactly does is that the traffic is going to actually flow like this. So from the pod to the OVN and BDB, it enters the host stack. So we have the management port, which is the key from the OVN into your host. And from the provider network, the FRR router, which is peering, will import the routes, copy it into the VRF. Each network is associated with its own VRF. So you see the route of the external provider network 172.20 appear in your routing table here, right here. And that is what is used for routing. So pod goes via OVN to the host. It sees this imported route and then leaves via the VRF to the outside. And for the import, we use the same API, which is the FRR configuration API. So we actually get what I mentioned was the import. For the export, also we use the same API like we said. So you can see that the blue networks subnet is already exported into the provider network. And the same thing is used in the second configuration mode, which is completely based off of OVN and OVS, called the shared gateway mode. But it's just a mode where we do not use the host networking stack, so as to say. So the traffic from the pod to the outside is always going to leave via OVS, so that all your flows are hardware offloadable. And in that case, the OVN Cube controller, this is the most important part, is just copying the routes from your VRF to the gateway router, which is logical router in your NBDB. And that's how the route looks like. So you can see provider networks route is then finally appearing in a logical router. And using that, we do the routing. And so now that you've seen this sort of, you might see the similarities between what Patrick mentioned and how it's done in OVN and how we're doing in OVN Kubernetes, with just copying the routes from the VRF into our NBDB. For us, NBDB, for OVN SBDB, it expects the CMS to program it in the NBDB. So that's the path that I said is done in the mode, in the shared gateway mode. And Jaime is going to cover the subtle differences and similarities between these two concepts of how it was done in OVN and OVN Kubernetes. Before I hand it over to Jaime, just wanted to say that we ended up in this crossroads because both the projects were doing this in parallel. We didn't know how OVN would end up doing it. We couldn't wait because we had timelines in OVN Kubernetes projects. So we anyways just did it. And then now, we are in this state. So it's a fun spot to be at. So take it away, Jaime.
Thank you, Surya. So this is us now, looking back, how we can go back and use OVN BGP support. And at the same time, we need to continue to go forward, developing additional features, BGP features. So pretty scary picture, right? So we see a number of benefits moving over to OVN BGP support. First of all, it's less of a burden for the CMS to use OVN BGP support, because you can imagine how handling the different events that trigger root configuration on the CMS and programming that into the BGP configuration is more complicated than just configuring a VRF to be advertised and let OVN handle all that for us. We also, another benefit is we would no longer need our custom implementation to import routes into the OVN topology, and less code maintainability and complexity on the CMS. We could also benefit in the future with the ability to advertise /32 routes, which is what OVN calls connected hosts. So that we have thoughts on how we can leverage this for some of our features. And of course, there is the benefit of being aligned with the community, so that we can benefit from future features, OVN BGP features, as well as being able to contribute back with ideas for OVN BGP. So we are going to, so when we looked on how we could move over to the OVN BGP support, we looked into a number of considerations. We looked into detail into each of them, but table ID management deals with the fact that we are introducing OVN BGP support on systems that already make use of VRFs. So we need to carefully handle table IDs. Also, OVN dedicates a VRF only for the control plane, while OVN Kubernetes has VRFs and uses them from the data plane. So we have thoughts on how we can make an efficient use of all of that. Default VRF support, OVN Kubernetes has a default port network that is associated with the default VRF. So it's also important to consider that when moving over to OVN BGP support. And then there is other subtle issues that we cannot really anticipate. But on an upgrade, we can think of a time window when the same routes are going to be managed by OVN and OVN Kubernetes, and is there going to be conflicts or problems just because of that? So table ID management. So I have two drawings here. The one on the left is simplified topology, OVN Kubernetes topology that we use right now. And the box in the right is how things would look like when we introduce OVN BGP support. You see that we have our tunnel keys already set on our logical routers, and we have our VRFs that already have table IDs configured on them. And you can imagine that when we introduce the OVN VRFs, they had to be configured with the same tunnel key corresponding to logical router, and you might find yourself in a situation that table ID is already being used by another VRF that you were already using, and that's not good. It's not easy to change the table ID just by a VRF. You need to delete the VRF and add it again, and that's this probably lead to disruptions. Equally, it's not easy to change your tunnel keys on a distributed system. In an upgrade, you're probably going to face network disruption. So I just have to thank LS again for that change that let us manage our own table IDs, and we don't have any of these troubles anymore. Moving on. So how does that network topology look like with all the VRFs that we will going to have in the system? So the bottom VRF is the VRF that OVN Kubernetes is already using. The top VRF is the VRF that we will introduce with OVN BGP support. And then depending on our configuration or the feature we're talking to, we're mainly talking about two data path flows, one that goes from the pods, logical switch, logical router, integration bridge, and to the outside world. And then we have another type of data path that logical switch, logical router, management port, and then a routing decision is taken on this VRF. So we have our BGP process, and basically all the routes that we learn through BGP are leaked into our VRF, and we use them for our routing decisions. And then when we think about OVN VRF, we would also need to import and leak routes to that VRF so that they are also leaked into the logical router, so they're also leveraged for this other data path. So you can observe here that for each of our logical networks, we have two VRFs, and we have a BGP process that needs to handle those two VRFs. So the logical thought that we have is why not just have a single VRF and share that VRF for OVN Kubernetes and OVN BGP support. So that would be more efficient. However, this is an example of the routes that we might end up with if we do that. And for example, on the first route that you have, that's a learn route that was moved from OVN to the VRF. Those routes, as Patrick said, are black hole. And those routes are not really useful for us to use them in the data plane, right? We need an appropriate next hop that is pointing to this logical router. So that's a change that we will need. The other thing that we observe is that OVN is going to take all the routes that haven't been exported by OVN itself, and they're going to copy over to the logical router. And that also doesn't work for us, because, for example, we have some routes here that we just want, static routes that we just want them there, but we don't want them on OVN. So basically what we need is to tell OVN which of the routes we want to OVN to learn. And the most straightforward option is probably to tell OVN, hey, just learn BGP routes, don't learn anything else. When we consider the default VRF, it's for us, or from this perspective, the default VRF is just another VRF. So the default routing table is just another VRF, and we will just have an OVN VRF mapped to the default VRF if we were not sharing VRFs, and in case we are sharing VRFs, it would just work in the same way. So just as a recap, the two things that we were considering, let the CMS manage stable IDs, which is already fixed. And then an open question for the community. What do we think about sharing the VRFs instead of having distinct VRFs for OVN and OVN Kubernetes? From our perspective, it's just more efficient. So it's a good thing that we could do. The extra support that we need to be able to do that is filter learning for OVN and actual next hops in our advertised routes. Another thing that we're thinking on for the future is to have more granularity on how we can configure OVN advertising process. So it's useful for us if we can do a per load balancer not opt-in or a per LSP opt-in to advertise as well as 32 routes. So that's all. Thank you.
Then thanks very much. It's really cool to see what happens to a feature that you helped build upstream and how it's now used. Are there any questions in the room?
Hello. Yeah. I also want to reiterate what Felix said. It's nice to see a feature we helped put into the world being used. So thanks. I actually have a question about how you configure your FRR, because I saw you exposed the configuration to the user, and presumably OVN Kubernetes makes some decision about table IDs and things like that. How will the user be able to produce the correct configuration if they don't have that information? Or yeah.
So the configuration is handled by OVN Kubernetes.
Okay.
Yeah. But it's also open to the user through the API to add its own configuration. So what FR Kubernetes does is that it takes all the configuration and it has a logic to merge everything in a way that it makes sense.
Okay, interesting. Thank you.
Yeah.
Hi. My question is that, so what I saw is that you have the CUDN configuration is there, which has the subnet, let's say some /16. And then you have the other CRD for advertisement where you're kind of pointing to the CUDN.
Mm-hmm.
So are you advertising that prefix, or is it like each node, whatever host slice it gets, locally advertises only that slice, which could be /24, for example?
So or different networks have different topologies depending on the topology of the network. So what we do is for layer 3 topologies, we just advertise the subnet that has been assigned to a specific node from that node. For layer 2 topologies, we advertise the full subnet on all the nodes. So what we end up in that case is with multipath routes being advertised outside.
Yeah, and cool thing we could reuse from Oven is the connected hosts for layer 2, where instead of advertising the full network from every node, we could reuse what Oven does and only advertise the hosts that are actually there on the nodes. So that would be very beneficial to us. And we cannot do it realistically from our implementation because it would be racy and hell to manage.
Does the OVN Kubernetes solution, right? It works in both IC and non-IC?
Only I see.
It's only IC.
Maybe now is the time to say when Kubernetes is deprecating non-IC. So
OVN Kubernetes is deprecating non-IC mode.
Hi. So from your slides, I learned that one VRF daemon is, one FR daemon is used for several UDRs, right? So how does it distinguish when it's receiving a route to which UDR it is, related? If it is used, yeah.
So we configure what BRF that route should be imported. So basically what we are doing is we have two modes of operation, right? One where we are advertising the UDN to the default BRF. So basically that means that all the learned routes on the default BRF end up on the CUDN. And then we have a specific configuration that we call BRF Lite, which we isolate all the CUDNs. And the way that we filter is because we have distinct BGP sessions on each BRF. So on the CUDN BRF, we establish a BGP session. All the routes that are learned through that BGP session only go to that CUDN BRF. So that's the way we do it, just different BGP sessions on each
different
BRF.
BGP sessions. So you're able to support IP address for overlapping, for example.
Yes.
Okay, thanks.
We're looking at this slide. We're way over time. A quick question. We're looking at this slide, and I was wondering if we implement everything that's in the second bullet point in OVN, will you guys use it this time?
Not gonna answer.
Okay, and specifically to actual next hops on advertised routes, how do you plan to do that? Those next hops need to be reachable on an actual Linux interface. If it's installed in a kernel table.
So they need to be, we could always have those black hole routes and add our own that are basically the same, but with the next hop that we want. But so in terms of data plane handling and routing decisions on that BRF, I guess that just having the IP address of the logical router port as a next hop would work. And in terms of advertising that route over BGP, BGP would replace the next hop, the actual next hop with the node IP address, I guess, hopefully.
Okay.
No, I guess time is up, and last questions afterwards, I would assume.
Thank you.